Greetings. In this one we will be talking about conjugacy classes and conjugation. So if we have a group and we have its elements, we can so-called conjugate them. So imagine we have a group G and we have at least two elements, G and H. So then if you want to conjugate element G by H, that basically means you put it into operation with H on the left side and H inverse on the right side. So that's called G conjugated by H. And now let's clear this and talk about a concrete example. But first of all, when we do that, let's talk about something else. And that is something called conjugacy classes. So when we have a group, it will get separate because conjugation causes equivalent. Conjugation is tightly connected to equivalence relations. And the groups, this underlying set of a group is partitioned into disjoint subsets that cover the whole group's set. Because conjugacy classes are partitions of the group. So by conjugation, one can partition a group completely, and so equivalence relations have certain properties, and those are symmetry, reflexibility, and transitivity. And these three properties are all fulfilled by conjugation. You can see that for any element, if we have a group G, then for any, let's write those out, for any G in a group G, any element G, we have, first of all, that an element is in the same equivalence relation with itself. So we can see it by this. If we take the identity element, we put on the left, and on the right its inverse, which is the same because identity element commutes with everything and its inverse is itself also. So let's see. Well, this is still G. So under conjugation we have this element E, an identity element in a group, and that causes it to stay the same if we conjugate an element by the identity. Then we also have reflexibility. So if we have A, G, for some A and B in also G, if we have A, G, A inverse equals B, and well, that's if and only if A inverse we could call that other thing could be H, but let's say now we leave it the way. Let's apply on this thing A inverse on the left side and A on the right side. What we will get is A inverse B A on the right side equals G. So we see that B conjugated by A gives G and G conjugated by A gives B. So we see that if one thing is conjugated in order to give another thing, that other thing is conjugated to give that first thing. So they belong to the same equivalence relation. So that's this other property. And then the third property is that we can sort of layer more conjugations on top of each other, which fulfills the third property of equivalence relation. And that is if we have G and we make it conjugated by A, by some element A in the group, well, that is, it's also possible to conjugate it by another element, let's say B inverse. And so what we get, that's going to give BA and then G. And if you have, we can just reorganize the parentheses, because as long as we keep this whole order, we can delete the parentheses where they were. And imagine A inverse B inverse on the right is in one parenthesis, but when we have two inverses in a parenthesis, we switch it and put the -1 exponent to that. That's the property of these inverses when doing this group elements multiplication. So we will get this same order BA also on the right side and all of that inverse. So as you see, if you conjugate by A and then you conjugate by B, it's the same as conjugating by BA. So we got that. So with this out of the way, now we've shown conjugation creates equivalence classes. So they're called namely conjugacy classes. And now let's look at an example. So we can have a group that's called S3, which permutations on 3 letters, so called. And I could write 1, 2, 3, 1, 2, 3 with the number notation, or I can also say these are ABC, ABC, it doesn't matter. It's called on n letters permutations. And I'm not going to go into what exactly this is defined as because this was covered in a previous one, but I will go into the example of taking the elements, namely there are 6 elements of this group, and identifying the conjugacy classes for an example. So I can write in this permutation notation, this is the identity element by the way, but the remaining 5 I will write as cycles because this is a long notation. So I will write those remaining ones as cycles, and namely they are AB, AB, BC, AC, ABC, ACB. Okay, you can verify for example BCA is this one, CBA is this one. So there's just 2 free cycles, and so we have 5 more cycles that I wrote out, and this is the first one. So in total we have 6 elements. Okay, these 6 elements. E, it cannot be written as a cycle because nothing changes under the identity permutation. And now let's identify the conjugacy classes. So conjugacy classes should separate this set out into disjoint subsets. And we know that the identity commutes with everything. So when an element commutes with everything, it will actually be a conjugacy class of one element. It will be an element that has it will be a one element conjugacy class. But elements that do not commute with the rest ones will generate larger conjugacy classes. So let's see first for the E. So what happens when I take the element E, I want to conjugate it by the other elements? Well, any element I take from G, I don't even have to say AB, I could say G, any general G, okay, is actually the same as if I said any general G because it applies. E has this principle that it commutes with everything. Well, the order changes and it doesn't matter for E, and so I'm stay with E. So no matter, and this is basically how conjugation is defined, right? If I conjugate E by AB, I put AB on the left and AB inverse on the right. That's the definition of conjugation. We've covered that in the beginning of this talk. So we see E stays in E. So no matter what we conjugate it by, be it AB or the cycle BC or the cycle AC or anything, or the 3 cycles, it will always stay as E. But other ones will not. There's one pattern that I will reveal here. For permutation groups, we will stay within the same cycle size. So it will turn out that E by itself is a conjugacy class. Then the 2 cycles are a conjugacy class. And the third and last conjugacy class in this one is the 3 cycles. So the size of the cycles with the same size are in a common conjugacy class. It turns out so. I could write it out and show it because this is a small group and there's not many elements. I could do BC or I could do AB and AC. So I will conjugate, for example, I will pick AB and I want to find its conjugacy class. So all the elements generated when it's conjugated by any of the remaining elements of the group. So I conjugate it by AC now. AC on the left and AC inverse on the right. Well, that gives BC. You can work that out by yourself, but BC is the result. And so you generate from AB, I know in the same conjugacy class is also BC, and I can also find that they are in the same conjugacy class with AC if I do some more operations, okay? I conjugate AB by BC, then I should get AC. I can show it. So when I conjugate any 2 cycle by 2 cycle, I stay within 2 cycles, and I cover the 2 cycles. So another conjugacy class are the 2 cycles. This was the first conjugacy class, disjoint from it is the 2 cycles, and disjoint from it are the 3 cycles, which are here. So now I can show that also. So I get to ACB and conjugate it by anything. Well, it will stay in the 3 cycles. So there's not much more space now, so let's just conclude it. And yeah, so for an example, we had this. S3, we listed the 6 elements and we found that in the case of permutation groups, the size of the cycle identifies the conjugacy class. The E, the identity element, is on its own, a conjugacy class of order 1. And then the 2 cycles are conjugacy class on their own, and the 3 cycles together make up a conjugacy class. Okay, where conjugacy class is generated by taking an element and conjugating it under this definition, or even more generally under this definition, of course, applying all other elements on the left and their inverse on the right to an element. And all that is generated will be other members of that conjugacy class. And so 2 elements are either conjugate to each other, members of the same conjugacy class, or they are members of disjoint conjugacy classes and not members of the same one.